the shape, the geometric shape. We don't like it, actually. It's not a real rectangular. So, but if you look at the connection, actually we can try to twist. You can twist the shape to real rectangular, just keeping the same connection. That will be fine, right? There's nothing different, just how you lay out on the plane. So just try to twist, okay? After you twist it, it should look like this. The connection, the wire are all the same, okay? Multiple y come from the top. Multiplier f from the left, for example, or the right, anyway, doesn't matter. And the product will be P0, P1, P2, P3, P4, P5, P6, P7, A bit. And this is the regular adder. Okay? Maybe curly for adder, maybe curly local adder. Either one of them. Alright, so that's the manual design. If you are interested, you might want to try to design and modify by yourself. Okay, just for exercise. I'm not going to, we don't have time to use the homework, but you can try by yourself. And that's the coverage for the final exam up to this point, to this page. Just reduce your loading. Because the next part is going to be more complex than this modifier. So, any other idea to improve it? This actually is a very fast modifier. The good modifier design is very fast. Just these are all conventional circuits. There's no flip-flop, there's no register at all, and just give it straight input, give it two input, two numbers, it will produce the product value. And by the way, here we have a critical path. If you look at the figure here, where is the critical path? Critical path means that where is the longest delay of the circuit. We have to consider that because that decides our speed, our circuit speed. So it shows here. Why? What is path? For critical path. We know that here we have propagation delay, right? That's the last bit you produce in the end. 这位是最后才产生的。This bit, the MSB of the product, is the last value you produce by the whole circuit. And there's a carry propagation here, but we have this 6A. These are in parallel, so no connection between this cell at all, the same row. So just from the top going down, the signal propagation from the top going to the bottom, and then through the typical adder, right? The clear path. And this is going to be short. It's very short. This is long. She said very fast. Any question? Now, we want to even improve. What can we do? Is there any idea, any technique that can even speed up the multiplication, the multiplier power? So, if you look at the figure here, we're doing CSA, element together from the top to the bottom, one by one, one point product, one point product, one point product. But is it possible that we can try to reduce the number of the class product? Here we have, I guess, 16, probably 16. The 16-bit multiple, 16-bit multiply. When you have 16-bit multiply, you have to have 16 partial product, 16 row. The more row, the lower delay. So how about it? We try to reduce the partial product to only one half, only 8 rows. How do you do that? Let's do this. Again, using the same example here, 1, 1, 0, 0, and 0, 1, 0, 1. Do the multiplication. How about it? We look at 2 bits at a time. For the multiply, 2 bits to times your multiple. Okay? Then you only get 2 partial product. In this case, well, that's easy because 1, 1, 0, 0, and then 1, 1, 0, 0. That's 0 result. Now only 2 partial products. But that suppose that we are able to do the multiplication by looking at 2 bits at a time. And 2 bits, there are 4 possible values. 0, 0, 0, 1, 1, 0, and 1, 1. Right? Each time 2 bits. So it could be 4 possible partial product. Zero, zero, 0, 1, 1, 0, 1, 1. Okay? Time you multiply. And we can look at each partial product. 0 should be easy. Just 0 or 0. 1, easy. Just copy the multiple, right? 2, easy again. Just shift left by 1 bit position. Adding another 0 in the end. Okay. Easy. Easy again. That's also easy. Adding 1 0 in the end. Shoot that by 1 bit position. You're doing double, right? 3, that's the trouble, guy. 3, how do you calculate? How do you get 3 times multiple? How do you do that? Is that easy? You can imagine that. Because why is that easy? 0, just all connect to ground, 0 signal. Just copy the same wire connection. Shift left 2, again, the same wire, just adding 1 0 in the end. But 3 times is not easy. The only way you can do it, you're trying to add 1 time, 2 times. These 2 add together, you can get 3 times. Alright? Is that easy? Addition is easy, but if you need to do addition, that's long delay again. We are trying to avoid long delay. So we don't want adding 1 time, 2 times, getting 3 times. No, that's not a good idea. So what can you do? Here's the design for, we are going to show that in a few minutes. Array multiply, the multiply design, require n partial product. If you look at group of R bit, here we are trying to look at 2 bits, but R can be 3 or more. But here, example, could be 2. Look at 2 bits at a time. We could form N over N divided by R, partial product. Right? If R is 2, we are cutting into half. Number of partial product. So it's possible that could be faster and smaller. We call that radius dash 2 to R encoding. Or here, in this case, if R is 2, radius 4. Radius 4 multiply design. So next we are going to show you how we design radius 4. If R is 2, it's radius 4. Encoding to do the multiplication. R2, look at here's the bit. Form partial product in the 0, y, 0, y, multiply. 2y, double the multiply. 3y, and first 3 are easy, let's say. But 3y require adder, which is bad. There is no delay, which we are trying to avoid. So any idea? We are trying to use boost encoding. Okay. Now this is kind of difficult, so listen carefully. Instead of 3y, try minus y. Then increment net partial product to add 4y. 4y minus y, you get 3y, right? But why did? Because minus y is easier to get than 3y. Okay? Minus y is easier to get. One complement or two complement. You can get a negative number. And one complement, two complement, okay, two complement is not that easy as one complement, but we are going to show you that how we do the design. But use minus y instead of 3y. But you owe 4y, right? You owe 4y. So in the next turn, next step, you have to add them back. Okay? Although 2y is also easy, but here we are using minus 2y. And then again, you owe 4y. You have to add 4y back. But the 4y is in next partial product. Let me give you an example. Example, like 0, 1, 1, 0, 1, 1. Okay. Now this is for the one part. And the one pen, 0, 1, 0, 1, 0. Okay. Let's say we look at 2 bits at a time. For the multiply. Okay. This is y. This is x. So there are only 3 partial products. The first one, 3 is going to be 3y. Okay. Second one is going to be 2y. Then going to be y. Right? So what's so good? But let's say, okay, 0, fine. Y, fine. 2y actually is fine, but 3y is a trouble guy. 3y is not easy to get, and then you have no delay. So instead of 3y, try to use minus y. We change it to minus 1. But you still owe 4y, right? 你欠了4倍，你用负 y 代替，你欠了4倍。So the next partial product, you have to add 1 y back, only 1 y, because you're shifting by 2 bit position. 你往左移了2位。You now look at this 2 bit. This 2 bit actually has a weight. The 1 0 actually 0 0 in the end. You look at the x multiplier, 1 1 here, is 3 times of y. 1 0 is here. Actually, you have 2 0 after this 1 0, right? 1 1 added 1 0 0, you get 1 0 1 1. So actually, this has more weight, 4 times of the weight. So 1 0 here, if you use minus y instead of 3y, you owe 4y. So in this 2 bit, you add 1y back. 2y now becomes 3y because of these 2 bits. Okay? Likewise. So here, instead of 3y, try minus y. Then increment next partial product to add 4y, but actually only 1y because of the shifting by 2 bit position. Similarly, for 2y, try to use minus 2y, and you need to add 4y back, meaning in the next partial product, add 1y back. Why we're doing this? Two bits at a time. These 2 bits in the multiplier, 1 1, or 0 0 1, 1 0 1 1. Okay, here's 1 1. But if this is 2 bits 0 0, the partial product should be 0. But this shows that if the bit position on your right hand side is 2i minus 1, 2i plus 1. This bit 0, just 0. Minus in this 1, meaning you owe 1y. If the bit on your right hand side is 1, you owe 1 multiple. You owe actually 4, but here only 1y adding back. But for the first 2 bit, you don't have to consider that because on your right hand side there's nothing at all. Nothing on your right hand side. But we have minus y here, 2y here. Okay, maybe okay. Maybe I should to the easier for you to understand. This is just 0. So before it should be 0, before it should be 2y. But as I said, on the right hand side, the bit is 1. The bit is 1. It means that you owe 4y in here, in this product, meaning you owe here for 1y. So instead of 0, it should be y. Okay. And then next, 1 0 here. If 1 0 on your right hand side, maybe 0, maybe 1. Here we have 0. So there's no, you don't owe anything. You just minus 2y. But again, assuming that you still have to consider here, virtually 0 0 here. Okay, and then you you still have to add it back. Okay, let me start completing in this table. We look at multiply 2 bits at a time. Okay, 2 bits, 2 bits, 2 bits. But you have to look at the bit on your right hand side in the next bit. 0, just regular result. 1, you have to add it back because you owe for 1 in the last step, in the previous step. In this step, you need to add 1 y back. So, if 0, just 0, pay product. 0, 0, but this means 1, you add 1 y back, so that's 1. 0, 1, that's 1 y. If it's 0, if it's 1, you have to add 1 y back. Y plus 1, you get 2y. 1, 0, that's 2y, but we say that try to use minus 2y instead of 2y. Because before it's 2y, but now using minus 2y, such that in the next term, this 2 bit, you add 1 y back. And 1, 0, that's 2y. But this means what? You owe 1 y here. So 2y, minus 2y. Then you need to minus 2y. Add 1 y back, you get minus y. 1, 1 is 0. 3y, you use minus y. But you owe for 1. 1, 1, here's 1. Minus y, add 1 y back, becomes 0. So that's the point product you're going to get in terms of hardware. Any question? Maybe this will give you a even more, even larger number. Okay, let's try to. Y is x. Multiply. And the number, let's give it a bit. Again, 2 bits at a time. Two bits at a time. So can you tell me how many project products do we have using what's encoded? How many? 4, right? You have 4 groups, each group 2 bits. So we call that radius 4 because let's 2 to the second. And the first project product, 1, 1 is here. On the right hand side, nothing here. There's nothing, so it must be here. Using minus y instead of 3y, because 3y takes longer to generate. 3 times multiply. But minus y is easier in terms of hardware representation, just using the complement representation to get the negative number or the multiply. So you have going to have minus y for the first partial product. It's going to be minus y. Okay? But we are aware that you owe 4y, right? Originally, you should get 3y, but you simply generate minus y. You owe 4y. But in the next two bits, 0, 0, because you owe 4y here, equal to you owe 1y here. That means 0, 1 times 2 to 6 bit. I'm sorry, yeah, 6 bit plus 1, 0 times plus 0, 0 times you see that? 0, 1, 1, 0, 0, 0, 1, 1. That's the multiply. So when you owe 1y here, in the second partial product, you look at this two bit, because the weighting is total second 是4倍的权重，这是权重是1而已。So here, you have to add it back instead of 4y. You only add 1y back because of weighting here. Alright? So the first term minus y. The second term minus y here. You owe 0, 0. You owe 1y in this to be position. So that's y. You get 0 plus y. The second partial product. How about it? 1, 0. 1, 0 is here. The right hand side bit 0 should be here. That should be 2y, but instead of 2y, give it minus 2y. Okay? But you need to add it back the next step. 0, 1, do it here. 0, 1, the bit on your right hand side is 1 here. Yeah? Meaning the previous step you owe 4y. So in this current step, you need to add 1y back. 1y plus 1y. That's going to be 2y here. And then you can add them together. Add these 4 plus water to produce new final result. And so, can you give me the reason why we don't just use 2y? Instead, we try minus 2y. What's the reason? The reason is that you want to look at S2y minus 1. The bit on your right hand side, that bit is 1. Meaning you need to add 1y back. 如果你右边是一个1的时候，代表你要么是10，要么是11，前两位是2或3，10是2，11是3，这样看的位元就知道你要加1倍回去。If you look at your right hand side, the bit, if that's 1, meaning you owe 4y in the previous step, equal to this step equals 1 y. And that's easy for you to implement in terms of hardware. Okay? From the calculation, it can be more complex, but in terms of hardware, that's easier to implement. Just look at this bit, you know that you have to add 1 y back. So pick one term, depending on your bit here. That's why you get minus y, y, minus 2y, 2y. Add them together. There are only 4 partial parts. Instead of the original design multiply, you need to have 8 partial products. And that's going to be faster than the original multiplier. Any questions so far? So, for the hardware implementation in the next page, okay, we are trying to generate these 3 y signals internally. If partial product 0, 0, 0, 0, 1 y, si, indicate 1 y, 2 si, this just name of the y, okay, this is not a real number, this is just a y signal, the signal 2 si, meaning 2y. N meaning minus, so minus 2y, this y is 1, this y is 1, minus y, 1y is minus. Okay. And 0, here is 0, the minus 0, but again, it's still value 0, but the minus, okay. Just look at the value here, the here, the minus 2y, minus y, minus y, minus 0, so this will be minus, will be 1. Use 3 y, these 3 bits can generate these 3 bits. Okay, so that's the typical combinational circuit. 3 input, 3 output. Okay, should be easy to design. And let's say 3 bit, 0 is 3 bit. Okay? And this circuit should be easy to design using the Boolean function. You can try to minimize, like column map, okay, to minimize the circuit. And after you produce this 3 bit, 3 y, this y is 1, indicate 1 y. This bit is 1, indicate 2 y. This bit is 1, meaning it is minus number. Alright? And again, this is an array. This is an array. The y comes from the top. Y I minus 1 is a bit on the right hand side. Yi is your bit position. The x from the top, from the right, the multiplier. 3 bit, look at 2 bit, the xi and x2i plus 1. This means your right hand side, okay? But anyway, you generate 3y indicating 1 copy or 2 copy, 1 time or 2 times, and plus or negative number. And that signal will go to the circuit here. If it's SI, just use YI goes through here. This is 1 AND gate. So this is just a multiplexer actually. This is a small multiplexer choosing if SI, YI goes through. If go to here, go to here. If 2SI, meaning shift left by 1 bit position. So multiply YI minus 1, shift left to this bit position. So it's here. And get here. If this bit is 1, then this bit will go through. So this is a multiplexer. Either choosing YI, YJ, or choosing YJ minus 1. Depending on either this bit is 1, or this bit is 1. Only two cases. And how about minus? If minus 1, mi is 1, meaning you have to complement. This bit complement this equal gain will invert the bit 0 to 1, 1 to 0. Okay, actually these two bubbles can be negated with each other and cancel them. They're very useful practice for manipulation. It is the control, it is the bit S 1. Equal symbol gain is just like a control gain. C is a control signal. If 0, S pass through. Alright? When C is 0, Y will be X. Just pass through. Is that right? 0, 0, you get 0. 1, 0, you get 1. So 0 is equal to 1. Just go through. When C is 1, the control is 1. You are getting S bar. You will try to invert the bit X. If 0, 1, you get 1, 0, 1, inverted. 1, 1, you get 0, 1, 0, inverted. So you see to control the input X to body output Y. If 0, just let it through. If 1, inverted. Is that okay? This is a very useful practice in the digital design. How about AND gate and OR gate? AND gate. Again, this for control. This input, this output. What is the purpose of the AND gate here? For the control. When C is 1, let it go, let it through. Alright? When C is 1, S0, you get 0. S1, you get 1. So S goes pass through. When C is 0, by the way, we are not going to cover that in the exam, okay? So don't worry about that. Okay? No boost encoding, no related for multiply in the final exam. So just up to the array multiply. Okay? Continue. If 0, no matter what value you have in input, you always get 0 in the output. Is that right? So AND gate 1, let it go through. Equals OR gate 0, let it through. How about OR gate? For OR gate, 0, 0, let it go through. Is C 0, 1, 1, 0, 0. If C is 0, C is 1, you always get 1 in the output, no matter what value you have in the input X. So let me repeat it. These three gates is very common when you design digital circuit to control some kind of gating. Okay, the control signal goes through. For AND gate 1, let it go through. But 0, always getting 0. OR gate 1, 0, 0, let it go through. 1, always getting 1. Equals OR gate 0, let it go through. 1, inverted from X to X bar. So here, that's the purpose of this equals OR gate here. when n is minus 1, you are doing one complement. Alright? One complement. Because that bit just negate, just for a moment, removing the two bubble here, 0, it will go through. Okay? 1, you are inverting. 0 will be getting 1. You are inverting. So that's one complement, right? When n is 1, we are doing one complement. 0, 1, 1, 0. If there's no two bubble here. But this bubble here, they cross out each other. 不得正. You have two bubbles, it's just like there's no bubble at all. But why? Why do we have bubble? Because no gate is easier to implement. You remember that? No gate is easier to implement than O gate. NAND gate is more easier to implement than AND gate. Okay. But because the equal gate here, the signal will go through. The two bubbles will cancel out each other. So just imagine that there's a bubble here, but this bit will invert the signal going through. So that's doing one complement. If this bit is 1, just one time the quantity. If 2x is 1, that you shift that. So this bit will shift to the left bit position to go through. So only one will be true. Either here or here. So only y, either yj or yj minus 1 will go through this 2n gate and go through the O gate, go through to here. But that also depends on mass and signal. 1, you're doing one complement, negated. 一的补数，再加复数. So that we go to the table we show here. You can get 1y or 2y, and it could be plus or negative. These signals indicate negative. The 1y will indicate 2y. Okay, let's do it.
哪一个？
这边比较复杂，所以我们就不考。那个题目好。
好。他这个对啊，他的意思就是说，就是再加 y， 这个是要加减 y， 或是加减2y。
那这边的这个比较左边这个也
就是说，
我知道他圈了，他把它分成两个比较，然后他说如果是3y的话就很麻烦。那我不知道3y是要干嘛。
3y的话就是它。你遇到3y，它就表示成负 y 啊，对吧？然后负 y 的话，是不是就是下一个这个加1就好了？因为它以2个嘛，以2个乘4嘛。
这边 道它这样子改成对称。
这样是负的啊。你说这个负2y 怎么得出来的吗？意思是这个吗？
可以说是这样。
就是他说他规定遇到2y 的时候要用负2y。
规定遇到2y 的时候要用负2y。这边这不是2y 吗？
对啊，2y 是表示要加2y 或是减2y。这个设1的话是要加2y或减2y，然后加或减是看这个 n，0的话就是正1
这
或负。
我知道，这边我知道，但是这个左边的原理不太了解。
对，它这个你就是，因为它都是看这个左边2个例子，你遇到2的话，它就是用负2y 代替，然后再下一层再加一个，再加 y， 是这样。
你是说如果这边遇到2的话，因为这样子是2，这边是2。
你遇到2y 就是用负2y 代替。
看懂他笔记在干嘛？
然后你如果2个 b 的右边那个，
就是最后边。
对1的话就要加1。
有这个我听到。应该呈现时代的。那你知道结构写的还好吗？
哪一个？
知道结构。我跟你玩之后我就死去。
我那个 map 没有打。
太麻烦了吧？
因为我觉得我前面，因为他用到那个红黑数，前面都没打。然后他说我这个，我就想说下礼拜那个，我再把那个 DFS 写完。
出来了。
对啊。
DFS 出来了。只是就是想他们出来最后一周变成你最后一周还要再来 demo， 就有点麻烦。
他下一周还要再出啊？
没有，这周最后30题，就我跟你讲1800。
我现在1800刚好。
那我觉得就够了。
是吗？
你赶快找他起 demo。
我已经1800了。对。
那就不要理他了，你不要写了，为什么要写？1800就不要写了，
他
不要搞不混。
真的1800是刚可以过吗？必过了。
对，因为你3000乘以0.6啊。
对啊。那你不是说要加？你不是说要加还是？你不是说要多一点？我现在是刚好1800。
他们有人会算17题，因为17乘以3.3。
所以是用3.3算。
对，是用3.3算。17乘以3.3，我现在不想算。对啊，17乘以3.3，然后56点。59.4。这小红说50几他都给过了，59那种。
所以是我不用写的，我不用写的意思。
我是觉得可以不用啊，你想写吗？
我还好。
你想写是
我想。
不介意啦。
我是还好，没有很想写。那我看来可以开始报读了。不用再写了。
我是觉得是可以的。等一下，我想一下。
我觉得老师讲的有点难。
其实我不知道为什么。
老师有点在讲，老师是从原理讲。
但我不知道原理要干嘛。
其实就是记组在教这个是为了要算有号数乘法。
有号数乘法，
然后跟加速乘法，就是跟把乘法加速。
我现在要加法跟乘法，我会想到大数相机。
不是，他刚讲我连做都没做。
你刚刚讲到大数，我直接联想到自己了。
我觉得你学这个3个 bit 要先去学2个 bit 之后，你才比较会。
这是3个 bit。
对啊，他是看3个 bit 啊，他有一个，最一开始是有看2个 bit 的。我知道为什么你没有印象， 上次都全部给我停课。他不是上次就是祭祖的时候，全部后面全部给我停课。我是自己去看的。
我没有认真。我那时候能活过就不错。
他第2章教完，第3章全部让你自己看，全部给我下那个不上课。
光看那document就已经看到发疯了，谁还会去看后面的内容？就是我在做他的第3个作业的时候，就在怀疑人生嘛。大家看卡派的作业。
上次是做地回嘛？地回我还有自己写出来。
现在就卡在这里，熟悉的画面是吧？就是这个是我的。
你现在是卡在社群的地方。
现在就卡在我要把我要从这边做地回一路这样走下去。对。然后是这边就是 analyze experience type。这里就是我想说，我把它用社学，如果它存在的话，我就去分析它的态。
对啊，就这样。这个不行啊。
就是它会一直走到很底层。然后就是现在有个问题是，它存 value 的方式有点重复，有点快炸开了。但是它的变数啊，它在存 type 的时候是用 I value， 这边的它的变数名字，这边，你看这边，它在存变数的时候，就是它的形态的时候，这个是一个0、1、2、3的参数，就是辨别它的形态。它在 type 的时候是靠 type 跟这个东西去辨别它是 int 还是 real 的形态。就是我在这边要辨别，然后但是这边的话是存它实际的 value， 就是假如说我 int r 等于10，那这边的10是这边是存那个10，然后这边的 I 是存 r 等于 integer type， 就是你说从哪里打开？反正他就是做了那个
比那个单词难。
我原本以为只要把它写出来，就是 pass 好就好，然后他还要我们执行 C code。还可以写。然后我刚才想说，把它的这个东西，就是全部都存在 R value， 后来想到不行，它的 R value 跟 I value 的那个的资料形态不一样。一个是 float， 一个是 integer， 这样它显示出来会不一样。但是把 int 存成 float 很长，妈妈不知道。我也想要把那个 integer 的 number 把它存成 float number。然后我打开。然后我刚刚还在思考说，yak 里面可不可以写 if else， 后来想说应该不行吧。yak 里面可以写 if else 吗？不行。
这样不行。
对啊，因为 yak 本身就是一个 pass， 就是转换语言功能，为什么我还可以在里面写死？还可以下面。那个快去写。
毫无想法。
我也想很久。我现在这边写完，明天就可以交 VLSI 破预售哦。而且今天交到15%。
加分吗？
对，而且我跟你讲，他这是更。之前不是点报告的话一起加15%，他现在变成只有提早 demo 加15%，他的书面报告不管什么，就是你只要在 deadline 之前上传，就是原分，它不是整个15%，它是只有 demo 成绩。
是啊。
对啊。
干了
超靠北的。我只是听到这规则，我整个翻笑。
太多行了。
不是，是
算太久。
不是觉得我的思考方式有 bug，就炸开，然后你也不知道它炸在哪里。就它的compiler每次都会炸在什么基底。
让我以后的工作不会碰到compiler，想到就好难。
希望如果往平面走，那就不会了。
我现在已经越来越觉得中央好像不错了，看来要去。
不想考。
我中央找那个老师做那个记忆体储存演算法。
我听到演算法不想考。听到演算法不想考。
那个应该是蛮，我那个应该是蛮厉害的。
就很厉害。
Okay, any question? It must be. Okay, let's continue. We are still in both encoding the multi type, this is 4. So let's say we try to reduce the number of partial product. Before we have 16 point product, and you look at 2 bit at a time. The 2 bit, the PP0, this 2 bit, right hand side bit 0 by default, and this 2 bit the next partial product. But look at the right hand side, either 0 or 1. So actually 3 bit determine one partial product. 2 bit is the main one you look at, but you have reference the right bit to decide whether or not you add one byte back. So you have the PP0, 1, 2, 3, 4, and up to PP7. But if this bit, this two bit might still owe 1 Y. So you need another partial product, PP8, and 2 bit here by default. So this bit 1 will mean that you need to add 1 Y back for this partial product. So actually, that's going to be 9 partial product. 1, 2, 3, 4, 5, 6, 7, 8, 9. The last one is the to augment, to complement the bit 1 here. Okay. But now we still need to solve one problem. We say that n is minus, so it will try to invert the value if value is 1. Inverting, doing one complement. But if you remember, one complement is not a real negative number. We are using to complement instead. So you need to add 1 back the bit. If you get it negative number, you need to add 1. Remember the designing separator? design the magnitude comparator B minus A for minus A. You're doing one complement, right? One complement. But carrying has to be 1. One complement and 1. That's 2 complement. Okay? So you need to still add 1 for the carrying. How do you do that? Look at here. S is the sign bit. These are all sign bit. It's doing sign extension, meaning sign bit is 1, these are all 1. Sign bit is 0, these are all 0. And if sign bit is 1, that's negative number, right? If negative number, you need to add 1 bit back. This is meaning the carry in 1. If sign bit is 1, that's negative number. So 1's complement plus 1, that's 2's complement, and that's real negative value you are going to get. So again, sign bit this way, 1 meaning negative number, okay? Extension, sign bit here, extension, sign bit here, the carry here, all the way. So that's what you're getting by the how we design using boosting coding. However, you look at, imagine that the circuit for sign extension, we don't like it. We don't like high fan out. Remember the some fan out? What I mean? Fan out means one signal going to connect many input, right? High fan out is not good because high fan out meaning high loading. Your signal has to drive high loading, it could have problem because if the driving capability is not good enough, you could get in wrong or ambiguous value. The signal, ideally it should be high voltage like 2 volt. But if loading too high, it could drop to like 1.5, 1.2, maybe even 1 volt. That's not enough because the driving capability is not enough because of high fan out. So we don't like high fan out. This is bad. How do you solve it? It's going to be equivalent to this one. Okay, let me try to copy the figure to here. Before we have this circuit, let's compare these two. We claim that these two are equivalent. Okay. We can use all 1 to replace the sign bit. Sign bit could be 0, could be 1. But why? Why these two are equivalent? Okay, give you 1 minute. Look at this. Why? Sign bit, the screen is still the same, so don't worry about that. Just look at this part. Why they are the same? Okay, sine bit, only two value, possible value, 0 or 1, right? If s is 1, then s bar is 0. If s bar is 0, then these are all 1. And we say that s is 1, right? So sine b is 1. It's going to be equal to this if sine b is 1. Or 1, 1, 1, 1. And 1 bar is 0. 0 is equal to 1. So these two are the same. How about s is 0? Then it's all 0. If s bar is 0, s bar is 1. 1 added to 1, 1, 1, 1. You are getting the overflow 1 and then all 0. That 1 is gone. Because there's no circuit to accommodate. You're getting 0, 1, 0, 4, 0. If s is 0, and s all 0, s is all 0, they are again the same. Likewise, for the other row, they are all the same. So these two are equivalent. But you might say that, wait, these are all halfway now. 1, 1, 1, 1, 1, all the way to the left. This is still halfway now. However, remember that we say that pulse prime is a very, very strong signal. Remember that? VDD and ground, they are very strong. So it doesn't matter. It has high thing now. The signal for VDD and ground is very, very thick, very wide. Not just 3 lambda, 4 lambda. It's going to be maybe up to 10, 20 lambda wide. So that's very strong driving capability. So it doesn't matter. You have high gain now here. Okay, now this one is better than this one. We're not done yet. You can still improve it. Okay, from here, okay, the sine wave are either all 0 or 1. Okay, and use that to reduce the loading. Okay, loading. And next is going to be equal to this one. Again, let me try to copy the figure. Copy this one. These two will be the same, will be equivalent. And y. Look at each point product. Again, the carrying sign is still there, so don't worry about that. Just look at these two. Y, they are the same. By default, they are all 0. Or 0, okay? Again, give you 1 minute. Look at this. It's not always actually. It's not easy to take a look and understand it right away. Okay, again, we are trying to manipulate this one bit. Is going to be added to the top. this one added to this number. So only these two ones are left. Keep those two bits. But this one added to this 1, 1, 1, 1, 1, it becomes all 0, and the overflow one is gone. So these are all 0. But how about this? The let me see. Okay, so this S bar is actually this S bar is again go up. This one gone, these are all gone, but S bar will come here. This S bar comes from here. But how about it? 1, 1 and S bar here? There are two possible values for S, either 0 or 1. If S is 0, okay, S is 1. If S is 1, S bar is 0. 0, 1, 1. So again, sign bit 1, 1 is the same. If 0, 0, 0, 0, you get 1. 1 added to 1, 1. You become 0, 0, and the left hand side is gone. So that's why you get S bar. Likewise, each row, the 1 will try to go up to cancel out this 1, and S1, S bar will go to this row. So likewise, each product you're getting it. And this one is better than this one because there's no high plane now. You don't need to connect so many wires from the bit. Before it's from sine bit, here it's from positive VDD, and now they are all gone. Only very low high plane now. Now this is better, even better in terms of hardware implementation. Or you can just say, try to pre-compute, because S has only two possible values, either 0 or 1. Plug two possible values, 0 or 1. You can get in the same result. You can also verify that. Okay, that's probably the end of the advanced multiplier design using the what's encoded, the version 4. Some people even doing some research on radius 8, meaning 3 bits at a time. That's even more complex. Okay, so we're not going to give you some idea. The researchers are trying to try every possible way to improve the hardware circuit such that it can be faster. All right? Even though it's more complex, but fine. Most of them give us more and more transistor. So we can afford it. We can use a more cheap area to design faster digital circuit. This example for multiply. Okay, and that's for a sign number. And for sign number, there are some modifications. We're not going to get into that. Higher value, as I said, could be 3 bits at a time, even more complex. And you can also compare the array multiplier to the 3 concept addition network to design a multiplier. Okay, that's about it for. But I said the final exam will be up to page 40, okay, up to this point, starting from the unit. I will never, but you can look at the unit system. more to unit 6, page 14. Any question? As I mentioned, after the final exam, the 18th week, well, the school actually it does not require we have a lecture, but because we have some missing hour before, so we are going to have to make up this class. It's up to you. You're free to join. It's not going to affect your grading. It's not part of the grading. So if you're interested, you can. We'll show the website on the e-learning after the final exam. Okay. We are going to cover the unit 7, explain how do we design the learning cell. Okay. We are going to distribute the technical quiz. 贴车小考。I haven't looked at that, but the TA finished waiting. Please take a look, and if any question you can ask the TA, and you have to return back. 薛玉化，薛玉什么东西？薛玉化那个，你们在那边哪些 ？Polo here? No.
这个是啥的？
No. 李义珍，谁生 ？Nora， 方彦纯，李方军，黄东升。Manual， 毛维亮啊，我觉得，Sataj， Nico， Pablo， 哪些？张平谦，江成林。 继承 ，Olin， 那些，陈彩英 ，Hesio， FIFA， 邱玉胜，
是啊，
薛玉化，So please take a look. I think the tea is quite nice. tea 应该给蛮宽敞的。If you have no question, you can return the quiz. "对于期末考范围没有什么疑问没有？我需要提供一些，比如你们可以问问题的时间吗？如果你们对期末考的准备有问题需要问我的话，我需要提供一些时间吗？需要的 ？No. Anybody？ 需要的 ？Okay. Let me see. 今天礼拜三，今天我们考，礼拜五可以，礼拜可以有一个时段，礼拜五2点到3点，下礼拜一 这题有2个时段，好不好？这2个时段，如果你们有需要问问题的话，2 time segment. Any question you want to ask me about the frame exam, can come to my office. Okay. If I'm not there, go to my lab. Okay. Either I'm in the office, which is 3, 12, in my office. If I'm not there, please go to A311. That's my lab. Should be in either places. Any question? 有问题？这是开放，大家可以问问题时间。If you cannot find me, okay, maybe should be around. Call me my phone number. You should be able to reach me. Okay. Alright, any question? If there's no question, we can stop right here today. So good luck on your final exam next week. Okay? 好，今天到这边。Please return